Hello everyone, I Nikhil welcome you to Vigyan Bharat. Today is our third lecture in the real analysis course, and we will be moving ahead with the notion that was just we started while concluding the previous lecture number 2, in which we discussed about finite and countable sets. Just a small information because today's topic is very important. It covers many very important topics, so I have to sometime go in Hindi somewhere in order for all of you to understand. Let me just show you quickly a glimpse of what is an interesting content from here. Starting from here, we'll be covering today. So I just want you, everyone, there is so many stuff coming your way and so many important stuff. So just I want you to just watch the video till the end, and whenever I ask you question in between, try to take a pause at there and try to answer yourself. And whenever if you have doubts over there, so you can drop me in the comment box. Okay, so let's begin with the lecture. As defined in the previous lecture, we were discussing infinite sets. Infinite sets are broadly divided into two categories. The first category is of countable set, which further has two subcategories. The first one is finite sets, and the second one are known as denumerable sets, or some authors also call it countably infinite. Okay, and the second type of infinite sets are uncountable sets. So finite sets, as I have mentioned here, already covered in the lecture 2. Now I'll be moving ahead with the notion of countable set. So this is an informal I would say meaning to this term countable. What it means basically, in this countable sets, we are interested to study either like countable set comprise of those, either they are finite sets, that is they have some finite number of elements, or they have the same size as the set of positive integers or the set of natural numbers. Okay, so we'll be covering this aspect in this video. Let's now move ahead. Just a quick recap of what I defined in the last lecture. Denumerable or countably infinite sets. So it was defined with the help of bijection map, which was very clearly explained in the previous lecture. What is the meaning of a bijection map? So what is the definition for a denumerable set? That given a set S, we have a set S, then we say that, try to listen very carefully what I'm saying. Try to listen it first. A set S is given to us. We say that it is a denumerable set or countably infinite set if we can find a mapping from this set S to the set of natural numbers such that that mapping is a bijection. What it means, that the mapping satisfies two conditions. The first condition is that the mapping is 1 1, and the second condition is the mapping is onto. 1 1 is also sometimes referred to as injective. Here I have just written 1 1 and onto. 1 1 is also known as injective in some text, and onto is also referred to as surjective. When any function satisfies these two properties, such a map is called bijection, or also is called bijective. Okay, so this was, in such cases we say that this set S is denumerable or countably infinite. Countably infinite means you can count the elements, the infinite elements of this set in terms of how you are able to count. You are assigning each element to a natural number through that one-to-one correspondence. Okay, now here I have explained this example in the last lecture, that this set E of 2n, the set of even natural numbers, forms a countably infinite set or denumerable set. You can understand this very easily. Similarly, this set of odd positive integers or odd natural number again forms a countable set. So this was very very briefly explained, very clearly explained in the last lecture. You may visit the explanation there. This was the result that if we take the union of two disjoint denumerable sets, then their union will be a denumerable set. Disjoint mean that their intersection is the empty set, that these two sets don't have any element in common. So their union, the resulting set, will be a denumerable set. So what I have just made an observation here, that the two examples which are discussed above, the set E, which comprise of the set of even natural numbers, and the set O, the set D here, comprise of the set of odd positive integers or odd natural numbers. Now if I take the union of these two, then the resultant set is the set of natural numbers, and which is a denumerable set using this result. Okay, and this is the rule how we can map these elements in general for any two A and B, and you can map the union with the set of natural numbers. Now in today's lecture and further lectures coming, the coming lectures, this notion of cardinality is very important, not only in perspective of this topic what we are studying, but throughout any course whatever you are be covering later on after real analysis, when we'll be studying say linear algebra or discrete mathematics, number theory, then this cardinality is very important concept. So try to understand it here itself. Okay, now the cardinality, we have heard this topic, we have heard this term cardinality. What is the idea? That we have a set and now we want to comment on the size of the set, how much large the set is. So let's study quickly what is the mathematical notion of cardinality. Observe that first I have discussed the case when the given set which I have is a finite set. Okay, so suppose I have a set S and there are exactly n distinct elements in S. Distinct mean that they are all different, and how many in total they are n. Now what is this n here? This n is a non-negative integer. Non-negative means something which is greater than or equal to 0. So either it may be positive or 0 itself. If it is 0, then in that particular case your set will be empty because it contains no element. If your n assumes some positive integer, then there will be exactly n elements in that set. Suppose, say for example, n is 7, then your set S contains 7 elements. And in this case, we say that this set S is a finite set, and this n is the cardinality of the set S, and it is denoted by this notation or expression. Okay, now here are some good exercises, very easy exercises, but you should try yourself. That in the part 1 you are asked to find the cardinality of the set A, where A is the set of all positive integers less than 10. Let me do it for you. I assume you will do the remaining ones. A comprise of set of all positive integers less than 10. Our positive integers are same as this set of natural numbers. They start from 1, 3, 1. They start from 1, but in this particular case, because A consists only of the odd positive, so A is this less than 10. So here easily you can see, you can even count that the number of elements in A, or the cardinality of the set A, is 5. Fine. Now you can answer this one. It's a very elementary exercise, very easy. And similarly this one, the set C. Try to answer me in the comment box. Okay, let's move ahead now. This is a very important remark here. Try to understand it very carefully before we move ahead to the notion of cardinality for infinite sets. What the remark says: we use the cardinalities of finite sets to tell us when they have the same size or when one is bigger than the other. It's very simple that whenever you have some finite sets, then in their context, in that context, when we are talking of cardinality, then we are interested we are interested to know whether they have a same size or they have a different size, that is one is bigger than the other. तो वहां पे हम क्या करना चाहते हैं, हम कंपेयर करके देखना चाहते हैं कोई भी दो सेट्स हैं तो उनकी कार्डिनलिटीज, अगर वो फाइनाइट सेट्स हैं तो क्या उनकी कार्डिनलिटी सेम है या फिर किसी एक सेट की कार्डिनलिटी दूसरे सेट से बड़ी है। तो उसमें जानने में हम इंटरेस्टेड होते हैं जब हम फाइनाइट सेट्स के बारे में पढ़ते हैं। ओके, सो नाउ लेट्स मूव अहेड। This is very important for today. I repeat again, try to understand this notion very carefully, because throughout in the lecture it will going to be used. So now we are moving ahead with the concept of cardinality when we are dealing with infinite sets. Infinite sets. Now I know what is an infinite set. A set which is not finite is called an infinite set. Okay, let's just quickly read this. We will define what it means for two infinite sets to have the same cardinality, providing us with this is a comma. Okay, so providing us with ways or methods to measure the relative size of infinite sets. तो यहाँ पे हम क्या कहना चाह रहे हैं कि हमारे पास कोई दो सेट्स हैं तो हम इंटरेस्टेड हैं कि क्या उनकी कार्डिनलिटी सेम है, या फिर हम और क्या कुछ मेथड्स को जानने में इंटरेस्टेड होंगे आगे कि जिससे हम क्या कर सकते हैं, जो उनके साइज हैं, वहां पे इनफाइनाइट सेट्स की बात कर रहे हैं अभी, तो जो उनके साइज हैं, मतलब उनकी हम जो कार्डिनलिटी के बारे में बात करेंगे दो डिफरेंट सेट्स इनफाइनाइट सेट्स की, तो उनके साइज के अंदर हम क्या कोई रिलेशन फाइंड कर सकते हैं, उसको क्या हम मेजर कर सकते हैं। तो उस तरीके से हम यहाँ पे इंटरेस्टेड होंगे पढ़ने में जब हमारे पास कोई दो इनफाइनाइट सेट्स हैं। We will be particularly interested in countably infinite sets. उसके अंदर भी हम कौन से सेट्स में इंटरेस्टेड होंगे, countably infinite, which are sets with the, this is very important, try to again, as I said, try to understand this highlighted point. जब हम countably infinite sets पढ़ेंगे तो वहां पे हम उन सेट्स में इंटरेस्टेड होंगे जिनकी कार्डिनलिटी सेट ऑफ पॉजिटिव इंटीजर्स या फिर सेट ऑफ नेचुरल नंबर्स के बराबर हो, एग्जैक्टली सेम हो। तो हम कौन से सेट्स को इंटरेस्टेड हैं पढ़ने में, काउंटेबली इनफाइनाइट सेट्स या फिर डिन्यूमरेबल सेट्स, जो भी हमने पहले भी समझा। ओके, सो इसके अंदर इसको अगर हमें पढ़ना है आगे, इसको समझने के लिए हमारे पास एक टूल है बहुत इंपॉर्टेंट अगेन, जिसको हम प्रीवियस लेक्चर से पढ़ते हुए आ रहे हैं, जिसको हम 1-to-1 कॉरेस्पॉन्डेंस बोलते हैं या फिर बाइजेक्शन बोलते हैं। Now, so we are going to use the concept of 1-to-1 correspondence in order to find the cardinality of two countably infinite sets in which we are interested. Now we should know what is the meaning of again 1-to-1 correspondence. So only you should know two conditions, that the function satisfy these two properties, that the function is 1-1 and the function is onto between any two sets which you are trying to define a 1-to-1 correspondence, or it is known as a bijection, which you are trying to define between any two given sets. Okay, so you should check whether that map possesses these properties or not. So the concept of 1-to-1 correspondence, as I mentioned again, was already covered in the previous lecture, so you may watch it if you haven't watched that concept. Okay, now we have some important definitions again in order to move ahead. The first definition says that given two sets A and B, we say that they have the same cardinality. A और B दो sets हैं, उनकी क्या है, same cardinality है, if and only if there is a 1-to-1 correspondence from A to B. What it means that if and only if, अगर एक आपको एक ऐसी मैप मिल जाए सेट A से सेट B पे जो क्या हो, एक by 1-to-1 correspondence हो या फिर bijection हो. Okay, so in that particular case we say that A and B have the same cardinality, and this symbol, this is a very important symbol, it means if and only if and only if. What it means, if and only if means two ways implications. This is the necessary condition and this is the sufficient condition. In this particular definition, if you assume this one, that your given two sets have the same cardinality, then using this information you try to prove that there exists a 1-to-1 correspondence between them. You can And if you are first assuming that the what I would say, this is called the necessary condition. Let me just make some so that you can easily see. Necessary condition, and this is called the sufficient condition. So आप एक को अज्यूम करोगे और दूसरे को प्रूव करोगे. तो सफिशिएंट कंडीशन में क्या होगा कि आप अज्यूम कर लो कि ए और बी दो सेट्स हैं, उनके बीच में सेम एक वन कॉरेस्पॉन्डेंस एग्जिस्ट करती है, तो आप वहां से प्रूव करोगे कि दे हैव द सेम कार्डिनैलिटी. ओके, दिस वाज द डेफिनेशन फॉर two sets when they have the same cardinality, and if that happens, then in that case you write that cardinality of A equals cardinality of set B. Now try to understand this next definition, very important definition too. If there is a one-to-one map, one-to-one function from the set A to the set B, then in that case, if this condition hold that you have a set A, you have a set B, you define a map from A to set B which is one-to-one or injective, then in that case the cardinality of the domain will always be less than equal to the cardinality of the codomain. This is a very powerful result again. The cardinality of the set A will be less than equal to the cardinality of the set B अगर जो आपका मैप है A और B के बीच में वो कैसा है, इंजेक्टिव और one और इंजेक्टिव. Okay, so this is definition 2 is true in general whenever you can apply this over any two sets A and B. Now very cool this group, what we are doing basically, cool diagram. So what I have done here, I have divided my infinite sets in two branches. On the left I have the sets, all those sets which have the same cardinality as the set of natural numbers. On the right, on the second branch of this infinite sets, I have all those sets with cardinality different from the set of natural numbers. Okay, so जो भी सारे sets हैं जिनकी cardinality same है as the set of natural numbers, उनको मैंने group 1 में डाल दिया है. जिनकी cardinality different है उनको group 2 में डाल दिया है. अब हमने यहाँ पे कार्डिनलिटी की बात करी सेट ऑफ नेचुरल नंबर्स की. जो सबसे जो बेसिक क्वेश्चन दिमाग में आना चाहिए कि जो हमारे इनफाइनाइट सेट्स हैं जिनको हमने दो ग्रुप्स में डिवाइड किया है based on the cardinality of the set of natural numbers. So what is the meaning of this statement, the cardinality of the set of natural numbers? What it means? Now cardinality, we mean by cardinality the size of a set. So how much is the size of this set of natural numbers? We have to answer this question. Okay, let's move ahead now. So this question is very important for us. Okay, to answer this question, we are now in group 1. Through the above here, we are now, to answer the problem, we are now in the sets which have the same cardinality as the set of natural numbers. So now try to recall again that we have already covered, that the countable sets are divided into broadly two categories. The first category is the finite sets. The second category is the set which has the same cardinality as a set of natural numbers, or which we also say them as countably infinite or denumerable sets. So वो सारे sets कहाँ पे आएंगे? Second category में. First category में कौन से आएंगे? सारे finite sets. Answer to the above question follows from here. Now try to understand this notion very, very carefully. Try to understand this. What it says, when an infinite set S, now what you are given, an infinite set S. When an infinite set S is countable, what it means that either it is finite or countably infinite, we denote the cardinality of S by this symbol aleph naught. I think here one typo is there. It should be countable, it's correct, but in precise what we are saying, countably infinite. Countably infinite, because it's obvious, it's correct. I don't have to write because you see this given set S is infinite. Only you have to distinguish when the set is finite. It is given that it is an infinite set and it is countable, so it directly implies that the set is countably infinite. So in this case, when such a set is given to us, its cardinality is denoted by this symbol, and this is called Aleph null or Aleph not or Aleph zero. Let me repeat again, but the symbol is called Aleph null or Aleph not. This is from where this symbol came from, the Hebrew language. This is the first letter you should know if someone asks you. And this is very important now. Try to mark this point. This is very important, that the cardinal number of n, this Aleph naught, is also called as the cardinal number of the set of natural numbers. So if someone asks you what is the cardinality of the set of natural numbers, you say that its cardinality is Aleph naught. And in general, now I'm answering your question. If someone asks you the cardinality of a countably infinite set or a denumerable set, let me be very precise, a countably infinite set. If you have an infinite set which is countable and someone asks you what is its cardinality, then it equals Aleph naught. In our case, we are given that S is countable and of course it was infinite. So in this particular case, we write that cardinality of S equals Aleph naught. Later on, we will be going to discuss in the coming lectures about when we're going to study uncountable sets. Then there also comes another transfinite number. Although I'm going to discuss it later on, but let me just tell you, it is known as continuum. So we're going to discuss it there. Okay. So I hope you now get a good idea what is the cardinality of the set of natural numbers. It is Aleph naught. Okay. Let me just have some water. Just a second. Yeah. So here is some useful information which I had this written. What you can do, you can pause the video and read it yourself. And no one will going to ask in the examination, but you may read it for an interest. Okay. Now here comes the math. Whatever we have studied now, it's important only when we can apply it. Okay. So now let's do this problem. You can see it in the example also, that I have taken the set of all odd positive integers, and my task is to prove that this set is a countable set. Okay, I have given the set of all odd positive integers. Odd positive integers means 1, 3, 5, 7, 9 and so on. This infinite many positive integers are given to me. Of course they are all odd, then I'm interested to prove that they are countable. अगर यहाँ पे हम ये शो कर दें कि जो ये सेट है और सेट ऑफ नेचुरल नंबर्स है, उनके बीच में 1-to-1 कॉरेस्पॉन्डेंस अगर हमने दिखा दिया, 1-to-1 onto मैपिंग, then we are done. ओके, सो यही हमने यहाँ पे इस डायग्राम में दिखाने की कोशिश करी है, अगर आप इसको ध्यान से समझ पाए. On the top, I have taken the set of all positive integers or set of natural numbers. अगर मैं natural numbers बोलूँ या set of positive integers बोलूँ, they are equivalent. Don't get confused. Now, see, this is our domain on the top, and this is our range set or the codomain. If you see, corresponding to every natural number, I am assigning a odd positive integer. Like my first one in blue here, this is I'm representing it as a natural number. Now here this one is a first odd positive integer. This is my second natural number. This is my second positive odd integer. Second means in the this list. Here I have given this set. This is given to me 1, 3, 5, 7. ये हमें given है यहाँ पे. So ये वाला जो set है odd positive integers का, इसमें इसकी second position है 3 की, जो कि हमारा 2 natural number को हमने वहाँ पे मैप किया है, 3 को 5 के साथ मैप किया है, 4 को 7 के साथ, and so on. तो ये हमने एक मैपिंग बहुत well defined मैप एस्टेब्लिश कर दिया natural numbers के सेट से odd positive integers के सेट पे. That is what we have defined. We have defined mapping which is both 1, 1 and onto from the set of natural numbers to the set of odd positive integers. And what is the rule? How it is defined? This is this rule, very simple. Fn equals to 2n minus 1. An odd positive integer is 1 less than an even number. What is an odd number? Which is 1 less than an even number. So here 2n represent an even number. I'm subtracting 1, so the resultant answer is an odd number, and n are coming from the set of all positive integers or natural numbers. So this is the map which I have established between these two sets, and which shows me that this set of odd positive integers is of course countable. Okay. So we have almost reached the concluding part of today's lecture. So before concluding, I just want you to again go through each, and let me just come at the end. I asked you to go through again through the exercises and to go through all the theory which we have discussed in this lecture. If you have any doubts anywhere, drop me in the comment box or in the Telegram group. You can find its link in the description of this video as well as in the about section of the channel. So just before concluding the video, two very good exercises for you. The first exercise is show that the set of all integers is countable set, and this is very important. If you are able to do it, then you have cleared half the stage of this idea of countability and countable sets. So try to prove this one, the second exercise, because if you are able to do this, then the later exercises which are coming in the next and further lectures, then this idea will be very going to be useful, but is used in the second exercise to prove that the set of all positive rational numbers is countable. So we conclude our today's lecture here, and if you have, as I repeat again, if you have any doubts anywhere, then do drop a comment in the comment box or in the Telegram group. You can text me there. And if you like this video, then please do give a like, and you may share about our initiative among your friends if you find it useful. And if you're new to our channel, then do subscribe it. And thank you so much for watching, and we'll be moving ahead with another interesting video coming on uncountable sets later. So thank you so much.